Aloha and welcome to this introduction to design patterns. It's going to be very high level, but hopefully will give you, the essentials of the concept, and then I'll have another screencast where I delve into specifics of the design patterns that you're actually already using in this class, but may not have been calling them a design pattern before. So what are design patterns? This term was defined by an architect called Christopher Alexander in 1977, and he says it describes a problem that occurs over and over again, as well as the core of a solution, at a level of abstraction where you can kind of use it in multiple contexts. So it's not specific to any, single problem domain. I like to summarize this by saying patterns help newbies acquire the hard-won experience of ninjas. So oftentimes design patterns occur or arise out of a lot of trial and error by experts over time, banging their head against recurrent kinds of things, and eventually the community kind of comes to a consensus about, hey, here's a typical kind of problem situation, and here's a good way that we finally figured out how to do it. And then you can read about the design pattern as a complete beginner to the area and go, oh, great, okay, now I know kind of how to proceed. So here's an example. There's, over time, I don't know, the millennia or something, humans have been creating roofs, and here's a few standard roof types that have emerged over time as having various strengths and weaknesses. And the thought experiment is to say, which ones of these would work, good in a place like Hawaii, as opposed to a place like Alaska. Some of these, like for example, the butterfly roof, which is down here, not going to work too well in a place where there's a lot of snow and ice in the wintertime. But I've seen one of those butterfly roofs right down my street in Hawaii, so you can do that here apparently. Okay, so how did design patterns come to be? Well, as I said before, they were invented by this guy Christopher Alexander in 1977. He published this book called A Pattern Language, and then via circumstances that I don't really understand, a group of software developers and researchers in about 1994 got a hold of that idea and said, you know what, that could really apply very well to the domain of software development. So let's build a book that talks about the design patterns that we're aware of that have emerged in the C++ community over time, or in various programming language communities, not just C++, but we'll provide a book which shows these design patterns and how you do it in C++, how you'd implement them in C++, circa 1994. This became this extremely influential, probably in the top 10 software developer books. It's often on your desert island picks or whatever, and these developers became very famous, and they're called the Gang of Four. And you'll often hear the Gang of Four book, or GOF, and if you're in the design pattern community, that that's what's being referred to. So with respect to software development as opposed to architecture or rooftops or whatever, the idea is that we're going to create some kind of fairly general and reusable solution to a commonly occurring problem in software design. And if we're talking about object orientation, then the pattern is going to show how objects and or classes interact together in order to solve this problem in a way that's generally accepted to be pretty good. Again, it's going to help a new person acquire the experience that was obtained through trial and error by their predecessors. So when we describe a design pattern, of course we have a name, and then we want to describe what's the situation where this pattern would be applicable, and then we show the outline of the solution, and then importantly we want to understand the consequences, which is typically what's good about this pattern and what might be bad. In terms of object-oriented design, there are typically three kinds: creational, structural, behavioral. So there's a lot of patterns about how you create objects, how you represent collections, and how you manage the interactions. In terms of the Gang of Four book, this is kind of the classic, they came up with 23 design patterns, and some of them apply just to classes, some apply to objects, some apply to both, and there are these kind of three categories. And I want to say, before you rush out and buy the Gang of Four book, it was written in 1994 and it uses C++. So whereas the high-level descriptions I think are still applicable, the actual implementation and so forth is a little dated at this point. It's a classic book, and you might want to have it in your library, just like the structure and interpretation of computer programs. There's some books that or the Mythical Man Month, like those are just books everybody should have, just because they're great. But in terms of actually applying this stuff to your modern code, there might be better ways. The other thing I want to note is that they initially were thinking just in terms of object-oriented design, and more specifically in terms of object-oriented design in C++. But once this idea got out there, I mean, everybody was talking about it in every single domain that you could possibly think of in software development. So, there were design pattern workshops for software architecture, for software processes, specific to a language, Java or Haskell or C++ or Lisp, stuff for user interfaces. Okay, and this makes sense, right? Because if you just think of design patterns as a way for people who have discovered in their domain a kind of template solution to a variety of, a class of problems, then that's a design pattern. And so obviously you're going to see them everywhere. So what I want to do now to make it a little more concrete is just go through four. And these are some of the most common design patterns of all. And so if you went into an interview and someone said, what's the factory design pattern? You shouldn't have like a deer in the headlights look on your face. You should be, oh yeah, sure, that's no big deal. I can tell you what that is. I don't know whether you'll pass the interview if you only know these four design patterns, but you can at least stumble along for a little bit longer. So let's look at the factory design pattern first. The idea here is we want to be able to create objects, and we want to, of course, hide the underlying logic associated with the creation, and then we want to have more flexibility than we would typically get if we were just using the object-oriented constructor, okay, which is kind of the built-in way to create objects in an object-oriented language. So what this looks like, here's a little UML diagram, and the idea here is that we're going to have this shape factory down here, and it's going to return instances of one of three different classes. Okay, so this is the first thing that this factory thing can allow you to do. In a normal object-oriented constructor, you can only return one type of object, the type of object that you call the constructor on. But with a factory, you get to return concrete instances or subclasses, for example, of a generic class, depending on your type system and what it allows. So you get this additional flexibility. That's just one of the additional flexibilities that you get. So the nice thing about a factory class over the standard mechanism for object creation in an object-oriented system is that you can return objects of multiple classes. You could even return a collection of objects, right? There's, a factory can do anything it wants. So, if you maybe it returns an array of 10 objects as a result of calling the build or the make method. And then very importantly, it can also create additional objects. So you might return one object, but in fact in the background you've had to create 14 other dependent objects in order to retain the consistency and integrity of the application as a whole. And a factory class or a factory object, factory method can do that and hide all of that dependent object creation from you. So the factory, you'll want this, right? I mean, it occurs all over the place in object-oriented design or in software design scenarios. I think the only disadvantage is, of course, it's more complicated than the object-oriented class constructor. So you should think for like 3 seconds before you use it and ask yourself, hey, do I actually need to make a factory or can I just use object-oriented class construction? Let's go on to our second design pattern called the Singleton. Probably the most the one design pattern that almost everybody knows about if they know anything about design patterns, and that's because it's intended to support the idea of a global variable in an object-oriented language where you may not have the ability to kind of declare an integer or declare a string or something to have it accessible globally. So how do we do that? We create a class and we ensure that only a single instance of that class can exist. And there's a variety of ways to do it with greater or lesser complexity, but that's the essential idea of a singleton, is that you have a class which will have exactly one and only one instance. So the advantage of this is that, oftentimes you want some kind of global state that's accessible to everybody, and you're implementing it in an object-oriented manner. It's, pretty simple to implement. It's pretty simple to actually implement in such a way that you don't actually create that singleton instance until you actually need it, which, might have some performance benefits. Disadvantages of singleton are that unless you take a lot of care with it, it will not be thread safe. And then secondly, it's generally not good to have global state. Okay, so because it's generally not good to have global state, it's generally not good to have a singleton, because that's what a singleton generally does, is implement global state. In fact, a lot of people call the singleton an anti-pattern, something you shouldn't do. And I'll talk a little bit more about anti-patterns at the end of this lecture. But if you need global state, if you're convinced you need global state in an object-oriented system, then the singleton pattern is the canonical way to try to do that. Next design pattern, observer. Again, you'll see this all over the place whenever you're doing event-driven. You're in a system where there's some kind of event-driven scenario. And this is the problem where you have a set of objects, we're going to call them observer objects, and they need to know whenever the state associated with some other object, we'll call that the subject object, changes. So basically the subject object changes, and then these observers should all do something or be able to react to a change in state to that one object. If you've ever heard of an event handler, or used an event handler, then you've used the observer design pattern, whether you knew it or not. So the typical way this happens is the subject object can maintain a collection of observers and provide a method so that some observer, if they want to know about changes to the state of the subject object, they can register themselves. So they kind of invoke a method of the subject object to add themselves to this observer collection, and then whenever the subject state changes, it knows to invoke this method called notify observers, which just runs through the list and calls the notify method of each observer instance, which is going to enable these observers to do whatever it is they want to do when that subject has changed its state. So this is a pretty cool pattern. You'll see it all over the place because it allows you to define a one-to-many dependency without tight coupling. Tight coupling would mean you actually have hardwired the names of the observers into the subject class. You can have two dependent objects, two observers, 200 observers, 2,000 observers. It doesn't really matter. And then even very cool, at runtime you could be adding and subtracting observers from a particular subject whenever the need arises. So it's a very nice flexible pattern. The disadvantages, you can have some performance problems. You can have race conditions in a multi-threaded system, and it can be harder to figure out what's going on when you have all of these notify methods being called in sequence, and they may have interactions and so forth. So the flexibility comes at a certain cost. There's always trade-offs, but generally this is a pretty solid design pattern. There's not a lot of times where you'd want to do something different from this if you have this particular situation. Let's go on to our fourth one. This is called model view controller. Again, almost like probably close behind the singleton pattern, maybe even ahead of the singleton pattern in terms of popularity. If you do anything with web application development, then you should know about the model view controller design pattern. In fact, if you do anything with web development, you're using the model view controller design pattern almost for sure. There are a few variants, but this basic idea is so ubiquitous in web application development, and even just general user interfaces. A native desktop app will use model view controller because it is such a it's such an elegant. In retrospect, it seems obvious, although someone had to come up with it, and before we didn't do it. But the idea is that when you're implementing a user interface, you'd like to separate the model, kind of the state of your system, from the way it's presented to the user. And the way we do that is we say the model is one component. That's basically like the database. Okay, the view is the presentation to the user. So that in Java that might be Swing for a native desktop app, or on the web it would be like your HTML and CSS and so forth. And then mediating between what's actually ends up being presented to the user and what's actually stored in the database is this third component called the controller. Okay, so here's what this looks like. You've got basically three components. You've got this controller, which is going to decide what view is presented to the user and how the state of the model is going to change. And when the state of the model changes, you're going to potentially refresh the view. So there's kind of a variety of ways that the event stream can occur in this, depending on the kind of variant of MVC, but that's the basic idea, is you have these three different components. Okay, and I think one of the coolest things about it is that if you think about developing a large web application, the skill set involved with presenting a nice user interface to the user is quite different from the skill set required to build a responsive, efficient, performant database system. And conveniently enough, the MVC model, MVC design pattern, has one component called the model, which is essentially the database, and another component called the view, which is the user interface. So now the actual design pattern, which is like an architectural design pattern in this case, neatly aligns with the kinds of skill sets that people in the organization actually have. So you can basically throw your database folks at the model, you can throw your UI folks at the view, and it's all G, right? They shouldn't be stepping on each other's foot, because then you'll have this third controller thing, which is mediating kind of the API that controls how these two things interact. So it's pretty cool. I got to say, pretty cool design pattern. That's why everybody uses it. The disadvantages, these are, yeah, it's a little complicated. There's some learning curve, but basically, just, you gotta just do it. You gotta figure it out, even though it's a little complicated, because the benefits are so big. And then I want to say that there are some variants of it, model view adapter, model view presenter, that kind of reorganize the basic responsibilities of these three components in slightly different ways. But for various situations, one of these other ones could be superior to MVC. I'm not trying to say they're not necessarily better, but really they're all kind of minor variations on this basic theme. Final thing I want to say in this brief overview is that if you've heard of design patterns, then you also need to know, at least have heard of anti-patterns, which is the idea, once people started thinking about, gee, this is the right way to do things, then some folks said, well, we should actually catalog as well the bad things, the terrible ideas that are out there. And so you can, Google around and find also, for any given discipline, you can, find anti-patterns associated with it. Here's just one example I picked out called lava flow, which is this notion: if you've worked on a system for a long, long time, if you've worked on a system which has been around for a long, long time, what you'll find is as developers come and go, things will be implemented, and then folks will start to forget, why is this way? What does this actually do? And since they don't know the answer to that question, they're reluctant to change it because they're worried that if they do anything with it, it might break the system in some unpredictable way. So the least risky thing to do is just leave it alone. Okay? And so the system starts to accumulate code which no one really understands why it's there. Or how it could be changed, and so they all leave it alone. And that's similar if you've ever seen a lava flow, which, you know, if you live in Hawaii, like I am lucky enough to do, you do get to see lava flows. And basically what happens is for a while it's molten and it moves along, and that's like fresh code. It's malleable, it's changeable, you can do things with it. And then after a while it cools down and it becomes rock. And, you know, it's solid stuff, very, very hard to manipulate, hard to change, etc. So that's where the lava flow name for this anti-pattern came from. Okay, that's my brief overview of design patterns. I hope you enjoyed it. Go out there, use some patterns. My next lecture, I'll talk to you a little bit about the patterns that you're already using in this class, even though you may not have known them as design patterns beforehand.